The other place that we sometimes see discontinuities is in piecewise defined functions. We're going to look at a couple of piecewise defined functions and determine the intervals on which these functions are continuous. Let's look at h of x first. H of x is equal to 4x plus 2 for x greater than or equal to -3. And it's equal to -2x squared plus 6 when x is less than -3. So in each piece, these functions are continuous. And so we know that they're going to be continuous for every number except possibly at an x value of -3, because that's where the two pieces are different. And so I know they're going to be continuous when x is bigger than -3, because when x is bigger than -3, that's just a polynomial function. When x is less than -3, well, that's just a polynomial function. So the only place that h of x could possibly have a discontinuity is when x is equal to -3. So let's check that out. So how are we going to figure out if this function is continuous or not at -3? I know it's continuous everywhere else. Well, we're going to look at both the left hand and the right hand limits. So we have to go back to what we did earlier, and that was look at left hand limits and right hand limits. The left-hand limit, if you remember, is traveling towards -3 from values that are underneath. So we're going to plug in our -3 into this bottom piece like we did earlier. And from the left-hand limit is -12. Let me do each step. So the left-hand limit is -12. The right-hand limit is going from above, so I can plug in -3 into my 4x plus 2. And I end up with -10. So what's that mean? Well, that means the limit does not exist. And therefore, we are discontinuous when x is -3. Just for completeness sake, I do want to say that if you plug in -3 into the function, you have to plug it into the top expression. So you would also have gotten a -10. And so all three of these have to match up to be continuous. If one of them doesn't match up, if either the left-hand limit, the right-hand limit, or what you get when you plug in the value don't match up, then we are discontinuous at that spot. And that means that this function is continuous from -infinity up to -3, and from -3 to +infinity, but not at -3. Let's take a look at this next one, w of x. We're going to look at both the left and the right hand limits, and then we're going to look at the function value and see if they all match up. The limit as x approaches 5 from the left of the function wx, since x is approaching 5 from underneath, I'm going to use that top expression. 10 minus 5 is 5. The limit as x approaches 5 from above, I'm going to use that bottom expression. 5 minus 4 is 1. And when you plug in 5, you have to use the top expression. You get 10 minus 5, which is 5. Well, one of these things is not like the other, and therefore, this piecewise defined function is discontinuous at x equals 5. It's continuous everywhere else, namely from negative infinity up to 5, and from 5 up to positive infinity. As a little note, I've been omitting the set notation for these sets. I've just been listing out the intervals. But if you want to, you could use a set notation of union. That means this is continuous at this place and also at this place. That's a set notation of union. Some of you may have seen that before. Just so you know, it is possible for piecewise defined functions to have a limit that exists and is equal to the output. Obviously, these two functions didn't satisfy that, but that doesn't mean there's not other piecewise functions that do satisfy that. What I'd like you to do at this point is pause this video and try to find the intervals on which these functions are continuous, or in other words, if these functions have any discontinuities.